Okay, good morning, everyone. Today, we'll be studying radar range equation. That's one of the simplified version of the radar range equation. Here is the outline of the lesson. You can see on the slide. We give radar range equation with receiver noise, and then we relate receiver noise with SNR. And then we define false alarms and detection process. Finally, we'll be discussing pulse integration. Okay, you might remember this slide from the previous lesson. This was the basic radar equation, and here we simply add some of the details of the parameter effective area here. This was not given in the previous slide. Now we define effective area of the antenna as the aperture efficiency times the cross-sectional area or physical area of the antenna. So if we are given a rectangular shaped antenna, which is very popular in surveillance radars, let's say with size of A and B, the area here is going to be A times B. While for a parabolic reflector, where we got a circular shape, typically the cross-section area is circle with a radius of r. So the area is going to be pi r squared. Okay, so A is simply calculated from the physical or geometrical properties or the geometry of the antenna. Now, next here, we are going to deal with this parameter, minimum detectable signal, and we try to relate this parameter with the receiver that we are going to use. Before that, let's see a bistatic radar system and simply give some hints on how to derive radar range equation for this system. As you see here, the transmitter and receiver are physically located far from each other. There is a distance here, let's say R3. And we have to write radar range equation here by using two links, one from the transmitter to the target and the other from target to the receiver. Since the transmitter and receiver are not co-located, they are not on the same side, we have to rewrite radar range equation here differently. Here, let's start as we did in previous slide. We start with the transmit power times the gain of the transmitting antenna, which is the transmitted power into the space. Okay, sometimes it's called effective radiated power, ERP. This travels by R1 and hits on the target. So the power density here is going to be PT GT divided by the surface area of the sphere at the range of target. So this is going to be the power density around the target. This power density hits on the target and reflected back with RCS of the target, and then travels again into the receiver now. So we can continue in that way. I'm going to leave the remaining to you. You can write range equation, and then we, at the end, finally, we should write the received power. Received power will be dependent on both R1 and R2. Okay, and the antennas here are different. So we have to use two antenna gain parameters or two antenna effective area, whichever you want to use. So the equation simply will be a little bit complicated. It includes some new parameters, different distance parameters, but basically they are it's very similar to the equation in the previous slide. Okay, let's see minimum detectable signal as min. It's simply the weakest signal, the smallest powered signal that we can detect by the radar receiver. Okay, so it's about the design of the receiver. Okay, not only the other parameters, but the design of the receiver. Usually, at the receiver, we got a threshold detection where we compare the received signal with a threshold, whether it exceeds that threshold or not, in voltage or power. If it exceeds the threshold, we report that there is a target. This is a target. If it does not exceed the threshold, it's below the threshold, then we report that that's noise, not a target. Okay, that's the methodology, the simplest method used in radar receiver. Now let's try to write minimum detectable signal in terms of receiver parameters. The most important parameter at the receiver is receiver noise, because it is a parameter that somehow constrains the detectability or detection of the signal. And can we use the previous radar range equation for practical designs? Actually, this is not possible. It was, as we said earlier, very simple form of the radar range equation. We have to consider many other parameters, for example, RCS, radar cross-section. It's not a constant number. It fluctuates, and it's highly dependent on the aspect angle, frequency, and some other parameters. We have to think about losses at the receiver and transmitter. There are too many cables and adapters or some others, some other components where we got additional losses. And there is also atmospheric effects along with the propagation path loss. There are some perturbations to the atmosphere depending on the frequency, operational frequency. You have to consider all of this, and then we couldn't simply say that the radar range is a single number. It's not a single number. We have to determine a range, and we have to define some other parameters. And the two of these parameters are probability of detection and probability of false alarm. Okay. Now let's see noise first and noise figure. Noise is usually due to the motion of electrons in conductors. If they move randomly, then they simply induce some voltage, which is called thermal noise. And it's dependent on the temperature of the environment. And then when we say noise or noise figure at receivers, we talk about thermal power. Mostly it's modeled as white noise. Noise power at a receiver, let's say we got a receiver here, and there is an input, and output. And the temperature here is T. Then the input noise power here is going to be K T B, where B is the bandwidth, T is the temperature, and K is a constant, and it's given in here. 1.38 10 to the minus 23 joule degree Kelvin. And T0 is given in Kelvin, by the way. Degrees in, not degrees in Celsius, degrees in Kelvin. And the bandwidth is the bandwidth of the receiver, typically IF bandwidth of the receiver can be taken. Then we can define noise figure for such a system. So let's take this as a system, and we got an input and output. Suppose that this receiver includes a simple amplifier, for example. If we model as an amplifier, we got an input signal to noise ratio here. Input signal to noise ratio and output signal to noise ratio. So noise figure of this amplifier or this device is simply the ratio of the input noise figure divided by the ratio of this is input signal to noise ratio at the input and signal to noise ratio at the output. Okay? This is the simplest formula for a noise figure or noise factor. Okay? Noise figure or factor. So, ideally, we expect that the output SNR is equal to the input SNR. So the receiver or the system that we are talking about adds no noise to the input signal. This is ideal case. So ideally, this should be unity or equivalently 0 dB. Okay. For an amplifier, we can write noise figure as this formula on the other end, where we have gain, as you see here, and the temperature, standard temperature of the receiver. And in the next slide, then we'll be deriving a minimum detectable signal in terms of this noise figure or the noise performance of the receiver. Any question? Okay, there is a problem here. It's a very easy one. Again, let's take, let's say a receiver, and we got an input SNR and output SNR. So the noise figure of this receiver is given as 2.5 dB, which is how many, how can we convert this into number? We take simply 10 to the power 2.5 over 10, right? This was, I'm sure that you know how to convert this, but just a reminder. So dB can be converted into ratio simply as 10 to the power dB value divided by 10. So if it is, for example, your noise figure is X dB, then this is equivalent in number 10 to the power X over 10. Okay? And X dB can also be calculated from x, sorry, x as 10 logarithm x. Okay, if it's x is given in ratio as a number, and then x in dB can be written 10 logarithm x. Okay, now in here noise figure is 2.5 dB. Okay, 2.5 dB, and the formula was S over Ni divided by S over No. This is given for ratio, okay, not dB. In dB we can write it, dB version is going to be S over Ni minus S over N out. Okay, so be careful when you are playing with power, noise, and voltage current in a communication system. Usually we use either numbers or dB, ratio or dB, or voltage or dB volt, watt or dB watt, microwatt or dB microwatt. So you have to be careful. If you are given dB values, it's better to use dB values, dB calculations or formulas only. If you are given numbers, what voltage, current, ampere, then you use numerical values, so standard formulas. It's a very important point. Most of the students may fail to switch between these numbers, and they may be confused and mix them up, and then the results will not be meaningful, not be reasonable. So from this formula, you can calculate, you can determine the reduction. The answer is inside the question, actually. Now let's see how to relate minimum detectable signal with SNR. Okay, we again take a receiver, and we got an input and an output. Here we got input power and input noise power, input signal power, input noise power. So the ratio is S over N input. Okay, at the output we got output signal power, output noise power, which is S over N output. Okay, now let's write the input noise power of the receiver. Input noise power of the receiver is simply, as we have shown in previous slide, K. If it is at standard temperature, it's going to be T0, B. Note that this is 290 degrees in Kelvin, and this is 1.38 10 to the minus 23 joule degree Kelvin. Okay, these are standard parameters if it is given in standard temperature. So the only thing here is bandwidth, as you see. So it's about the radar design, actually. So we determine B according to the mission of the radars. Okay, so that's a design parameter. And we know that this bandwidth is related to the pulse width, inverse of pulse width. So that's a design parameter. The others, the remaining, are simply standard numbers. Now, we can write then the input signal power as, we can write this as, here, this is going to be the noise power times the noise figure, S over N output. So simply, we remember noise figure. What was that? S over Ni divided by S over No. I just use this here and take this S in. Take this S in. So S in is going to be Fn S out over N out times N input. Okay, so this formula. Now, the input noise power was given with this formula. So the input signal to the receiver can be written in terms of what? Bandwidth. Okay, let's take a look at the parameters in here. We have bandwidth, we have noise figure of the receiver, and output signal to noise ratio. Okay, again, let me write that. The input power is going to be KT0B, which is the input noise power, times the noise figure of the receiver, and then output SNR. Okay. Now, at the maximum distance, so the range, okay, for radar range, we get minimum signal power. Okay? So then what happens if I take, okay, if I take the input as minimum signal power? That's my objective in radar range equation, because in radar range equation, we got S min. And now I am trying to write S min in terms of other receiver parameters. Okay? And it's written here. Next, then, if I take the input signal power as minimum signal power, then the output SNR will be minimum. If I define this minimum input, then I define simply SNR output minimum value of SNR output, so that I can write this into the radar range equation. So simply we write output SNR minimum. We equate output SNR minimum to output SNR, so that the input signal will be minimum detectable signal. In that case, we simply replace this input signal power by minimum detectable signal and replace this output SNR with SNR minimum. Okay? Is that clear? Then we can insert this into radar range equation. We have already got a radar range equation, simple radar range equation. Now we insert this equation into there. This was the radar range equation we derived in previous slides. Now we replace this S min, minimum detectable signal, by this equation or this equation. So the new radar range equation becomes like this. Here, we have added some new parameters here, right? One is the bandwidth, which is not available here. And the other one is noise figure, not available in the previous version, and minimum SNR. Now, we simply replace minimum detectable signal by these three parameters. We extend it. So what happens then? We actually, here we have written equation which is independent from the radar receiver noise, okay? Because receiver noise as a function, as a parameter, appears in this equation, okay? Now, next, we'll see how we relate this minimum SNR with two new parameters. These are probability of detection and probability of false alarm. As we said earlier, radar range equation is not actually a single number. It has a variation. because the RCS varies with the aspect angle, with the frequency, some others. And there may be variation on the atmospheric links over the links. So then the range will be varying depending on the target position and the link. Okay, so we talk about then probability of detection and probability of false alarm, and then relate these two parameters with the SNR, minimum SNR. Okay, so in next slides we'll be studying this. Here we have a problem, a very simple problem. We simply use this equation, insert all these numbers, and then determine the maximum range. So you see here, we got some dB values and some numbers are not given in dB, some parameters. So we have to be careful here, okay? When we use this equation, we can, for example, write this equation in dB, okay? PT plus G plus AE plus sigma minus 4 pi squared minus K minus T0 minus B minus Fn and minus S over N minimum. Okay, this is one way to write it in dB. If you convert all parameters into dB, then you can use this equation. That's going to be summation and subtraction. Is that clear? And it may be easier in some cases. Or you can insert all these values into here. For example, SNR is 20 dB. 20 dB SNR means 10 to the 20 divided by 10, which is 100. So I have to insert here 100. Similarly, if the noise figure is 3 dB, if the noise figure is 3 dB here, 3 dB means 10 to the power 3 over 10, which is 10 to the power 0.3. So you have to insert in this equation 10 to the power 0.3. Okay, so you have to choose carefully whether you use dB, all dB, or all numbers. Okay, if you mix them up, you will get trouble. Okay, now let's see probability of false alarm and probability of detection and the relationship between SNR minimum or SNR simply. As we said earlier, one of the most important parameters of a radar receiver is noise figure. So noise simply is very critical. So here we'll be evaluating what happens if we got a noise at the input of the radar receiver. If there is no signal, echo signal coming from the target, then we expect noise is coming into the receiver. So what will happen then? Here we show what happens if we got a Gaussian noise at the input. Let us first go back to Gaussian process. A Gaussian noise can be illustrated just like a voltage, randomly varying voltage. This is, let's say, time, and this is V of t. I'm sorry, there is a problem with this pen, I think. Now, suppose that we got a noise here, randomly varying noise. Okay, there is no signal here, just noise sampled over time. And if we look at the probability density function, of this noise, we'll see something like this. Okay. So the average here is 0. The mean value is 0. There is a variation. There's a variation here, right? So this is the mean value. This variation can be written in terms of standard deviation. Okay. So higher the variation, higher the standard deviation, and higher the variance. Okay. So this is how we define Gaussian noise. It's added on any signal. This is the PDF. Okay. Now, suppose that we apply this noise into IF stage of a radar receiver. In IF stage, we got a combination of filter and amplifier. Usually, it's implemented as matched filter. Okay, we have already studied a matched filter in where? Do you remember matched filter somewhere? In communication systems, do you remember convolution, correlation? Where we got two rectangles and then convolve them. It was convolution, and where we actually mentioned about match filter. Anyway, match filter, we'll be talking about that in detail. That's one of the topics that we'll be discussing toward the end of the semester. At the moment, just imagine that that's a filter, okay? That's a filter that maximizes signal-to-noise ratio, okay? So let's say here we got a SNR input, and here we got SNR output. So match filters maximize this SNR, okay? That's a filter such that it maximizes the output SNR, okay? So we'll be discussing how to design such a filter. That's the subject of the one of the lessons towards the end of the semester. So what will happen if I apply a Gaussian noise to this match filter or IF amplifier filter section? We are not going to give the details, mathematical details, derivations in here, but it's very well known that if we apply Gaussian noise into this system, the output will follow Rayleigh type PDF. Okay, the output signal follows Rayleigh PDF. Its amplitude follows Rayleigh PDF. What is Rayleigh PDF? Here is the Rayleigh PDF. Here we got mean square value, M2, and standard deviation, which is 0.5. And here is the picture of Rayleigh, in Turkish Rayleigh PDF. You see, this is not symmetrical. This is always positive because that's envelope. We get magnitude square or magnitude, then it means that we got positive values only. So this is the envelope of the output signal. Okay, it starts from 0, goes, make a pick in here, the distribution, yeah, not the signal itself. Okay, be careful. That's the distribution of the envelope of the output signal. So when we apply then this signal, then we can simply show the output here. So if this is the line, then this is going to be just like this. Okay? So this one is this one. It starts from 0, as you see. Okay? This is the output distribution. Okay? It starts from 0. And it has a peak value somewhere here. So most of the values at the output is concentrated around that peak value. So this shows simply what happens when we apply a Gaussian noise to an IF stage, okay? Mathematically, we now show that the output signals envelope follows Rayleigh PDF. This is important because in next stage, we'll be looking at probability of false alarm. That's the parameters that we have been talking about. It's very much related to this Rayleigh PDF. Okay, let's go back to the radar receiver. Here, we see some portion of the radar receiver. You might remember there is a mixer in here. Here is the RF signal. Here is the local oscillator. Usually, this is a voltage-controlled oscillator, which is the subject of Friday's experiment, as you might have studied that. So this is a very critical component in especially FMCW radar system. Here we use a local oscillator only, not VCO, because we need usually here single frequency signal. So the output will be the IF stage, applied to IF stage. Now at the IF stage, what do we have? We got a match filter here. As we said earlier, this was the IF stage in the previous slide. And following this, we got a second detector. Usually that's a diode detector. And then we got a video amplifier. Okay? So what kind of signal we expect here? Here, we got a high frequency sinusoid. Okay? And it's pulse modulated. Now, after mixer, this is down converted. So the frequency of the cosinusoid is reduced to some reasonable level that we can process. And then we got a match filter. So the output of the match filter is typically, if the input is just a sinusoid like this, then the output of this match filter will be something like this. I will try to draw it, but I may not be correct. Okay. Again, a sinusoid, but its envelope, you see, is not constant. Just like this. Okay. So here is the output here, and this blue one is the illustration of the signal right here. Okay, and the red one is the input to IF stage. Okay, so similar. This looks like this, not exactly, but looks like this. Here we have no noise. If we add noise, that's going to be quite complicated. Okay. And after video amplifier, of course, we'll have stronger signals, just like this, at the output of the video amplifier. And then we got a threshold detection, where we have a threshold. Let's say we set a threshold here, and take some samples in here, 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 here. Okay, and compare with the threshold. If it exists the threshold, we declare that there is a echo signal. If it does not exist the threshold, we declare that that's a noise. Now, the thing that we are dealing here is that what happens if there is a strong noise at the input, or if there is a clutter from the environment. not an echo signal, not a target, but an echo, a clutter signal or noise, strong noise at the input, which may cause false alarm. Okay, false alarm. So here is the illustration. So at the output of the video amplifier, we got such a voltage waveform. Here is the time, here is the voltage, and we got a threshold here. You see the threshold in here, and the root mean square value of the noise. So the mean value of the noise, let's say, somewhere here. Okay, so there are 3 points here where we take samples and compare these samples with the threshold. Okay, at point A, you see it's quite apparent that this value exceeds the threshold. Okay, so it's likely that that's an echo signal, a target signal, because it's quite above the threshold. But it may not be. But now it seems that this looks like a target signal. How about B? At B, you see that's about the threshold. We are not sure about whether that's due to the target or noise only. Okay, and at C, it's just below the threshold. It's likely that that's a noise. Okay, but not sure still. Now we can define false alarm and misdetection on this picture. If the signal at point B, if the signal at point B is due to the noise, if this is noise actually, but if we declare that's an echo signal because it's just about the threshold, then this is called false alarm because that's not an echo signal. But we decide that that's an echo signal. So that's called false alarm. Okay? If, for example, let's see the point C, if this will be an echo signal, but we declare that that's noise, then that's going to be misdetection. Misdetection. This is actually a signal due to the target, but we decide that that's noise, which means that we missed an echo signal. So that's called misdetection. Okay, misdetection. Now, this might happen in any radar system, and it happens frequently. And then we have to be careful on choosing this threshold value. If we choose that threshold value low enough, then we can report more false alarms. Okay? If we increase this threshold much, then we'll have many misdetection. Okay? So there should be a compromise. There should be somehow a logic here how to tune this threshold. Okay? And it's very much related to the noise level of the receiver or clutter in the environment. The best way is to choose this threshold adaptively by inspecting noise over a time and determine the mean value of the noise and then choose the threshold. So monitoring the noise, get the average, choose the threshold. Monitoring noise, get the average, choose the threshold. That's called constant false alarm rate radar, CFAR radar, where we try to fix the false alarm by tuning that threshold adaptively. It's used almost every radar system now. Now, we have already shown in previous slide, if we have noise, Gaussian noise, at the input of an amplifier, IF amplifier, the output follows Rayleigh PDF. So Gaussian signal enters, and we got an output signal whose envelope follows Rayleigh type PDF. Now, if we got a noise and the output signal exceeds the threshold, as we said earlier, that's called false alarm. Now, let's try to calculate probability that the measured signal is above the threshold. So, probability of false alarm. This is simple formula for that. We can now go back to the PDF of Rayleigh signal. This was just like this. That's the PDF of Rayleigh signal. Let's say R, not X. Now, probability that R is greater than the threshold, but less than infinity. It may go up to infinity. So here is infinity. The values may go infinity. Theoretically, in practice, there is no infinite value here, but theoretically, it goes to infinity. So we try to determine this probability, which is probability of false alarm, because we got noise at the input. If we got a signal exceeding the threshold, this could be a false alarm. So this requires simply integration, evaluating of these integrals. And this means that if we take here Vt, okay, we actually here determine this area. Okay? We determine this area. Now, we are not going to give the details here, just if we can do it actually. This should be inserted into this integration and then evaluated. You will get this one. So here is the probability of false alarm. It's dependent on what? The threshold voltage and psi 0, which is the RMS value of noise. Signal threshold and RMS value of noise. Usually, this will be taken as the corresponding SNR, okay? Because one is Vt is signal Vt squared gives you power, right? Voltage squared is power. So the power of the signal divided by psi 0, which is the variance. So RMS value of the noise, which refers to power of the noise. So this ratio is simply the signal to noise ratio. Okay, let's have a break here. Okay. Now let's look at how we see false alarm time and rate. Here we see the signal at the output of the IF stage, IF amplifier, envelope of the noise voltage. Remember that we assume IF amplifier, and we got Gaussian noise, and the output is it follows Rayleigh PDF, the envelope of the output. Now we look at this envelope signal of noise voltage. The false alarm time will be the average of the TK here we got one false alarm in here, just an illustration, here and here. So there is going to be time interval between the false alarms, and if we get the average of this, we determine false alarm. Statistically, that's correct. When we take infinite number of false alarms, and if we get the average, then we determine false alarm time. Probability of false alarm, on the other hand, will be related to the interval in which the signal, the envelope of the noise voltage exceeds the threshold. That's the duration of that signal. And the average of that signal to the average of the false alarm time will give us probability of false alarm. Okay, and it's related to the false alarm time along with the bandwidth. Why? Because the bandwidth, as you might remember, was related to the pulse width, pulse duration, and we expect that Tk, the average of Tk, will be the pulse width. Okay, that's the minimum duration that we consider in the radar system. So then we can write false alarm time in terms of bandwidth and SNR. Sorry? 15. No. Oh, I'm sorry. Okay, I'm sorry. Let me share again. So here, now you can see, right? Okay, so we are still on the same slide, by the way. I did not change anything. But you have that slide with you, right? From PDF, do you have it? Okay. I'm sorry about that again. I didn't know what happened, but okay. So false alarm time can be related to then two parameters. One is the bandwidth, the other one is SNR, or VT squared over 2 psi 0. Here the bandwidth is related to the pulse width, inverse proportion, and it defines the IF bandwidth, intermediate frequency bandwidth of the radar, which is the bandwidth of the radar. Usually, probability of false alarm is very, very small because that's expected, of course. It is high, then we will get trouble with the radar. Usually, we talk about 10 to the minus 6 or 7 or 8, which is one out of every 1 million pulses, 1 million decisions. So we may get false alarm out of every 1 million or 10 million pulses. Remember that pulse duration is very, very small, on the order of microseconds. So one false alarm out of every 1 million decision means that with 1 microsecond pulse duration, it means that one false alarm in every second. So that's big for us. Small for us, but that's big for a radar system. In every 1 second, one false alarm cannot be accepted, maybe. So we usually reduce this number as much as we can. So here we got a graph with many curves. These are the bandwidth, okay? And here we got threshold to noise ratio, which is proportional to signal to noise ratio, as we said earlier. And on the vertical axis, we see average time between false alarms. So that's TFA in R, and TFA on the right-hand side converted to some time units, minutes, hour, day, week, month, and year. Okay. Here, as you can see, if we change SNR, we expect the average time between the false alarms increase. Okay, so we get less false alarms, and we can show it in here. For example, if we take an SNR of 13 dB for 1 megahertz bandwidth, so this is 1 megahertz bandwidth. As you remember again, bandwidth is a design parameter and we tune it. Okay, we determine according to the requirements, according to the mission of the radar. So if we choose bandwidth, then we can next talk about SNR, how much SNR we can tolerate or we may need. And then we can determine false alarm rate. If it's not acceptable, we increase SNR. Okay, or we change bandwidth, whatever we want. So here for 13 dB, the false alarm time is somehow, if it is hour, then that's going to be 0.2 hours approximately. Okay, so it's about 5 minutes maybe, or 10 minutes. Okay, when I increase this to, let's say, 13.5 dB, so somewhere here. Okay, the same curve you see. Now it was about 10 minutes. Now it becomes 1 hour. Okay, so half a dB increase in SNR simply increases the false alarm time more than 6 times. Okay. So this SNR value, as you see, is very critical. That's a parameter that we can tune to achieve desired false alarm time or false alarm rate. By the way, once you know the false alarm time, you can easily switch false alarm, probability of false alarm. Okay, PFA and TFA are related to each other through the bandwidth. So whenever we say false alarm time, average time between the false alarm, you simply remember that that's probability of false alarm. Now, if we have a false alarm, it does not mean that that's a reporting of a target, because mostly we look at the number of false alarms, and if we repeat this, and then we we report a target. Okay, so false alarm does not mean that reporting a target to the operator. We have to be careful in here. Now let's go back to the IF system again. In previous 3 or 4 slides, we evaluated Gaussian noise at the input of the IF amplifier, IF stage. Now we add echo signal. Echo signal plus noise. So previously, simply, let's try to illustrate this. For Gaussian noise only, we got noise only, okay? Here is time, here is voltage, and we got noise. Now, what happens if we got echo signal? Then if we got echo signal, then this becomes like this. Okay? This is signal plus noise, and this is noise only. Okay, so we are now evaluating these 2 cases. What happens when we apply signal plus noise to the IF stage? What happens if we apply noise only to the IF stage? For false alarm rate, we apply noise only, because false alarm as a definition is about reporting of false alarms due to the noise only. There is no echo signal. On the other hand, when we got signal plus noise, we talk about detection probability. How well we detect the signal with noise. Okay, so that's why we consider these two cases individually, separately. In noise analysis, we talk about false alarm, signal plus noise at the input of the IF. We analyze detection probability. So what happens if we have such an input signal at the output, on the output of the IF stage? If we got such a waveform, the output signal envelope follows rise in PDF. Okay, so the previous one was Rayleigh. Now that's rising. Here is the probability of detection then. At the input, we got a sinusoid, typically, plus noise, as we have shown in previous slide. And the envelope at the video output follows rise in PDF. Rise in PDF is a little bit complicated, probably the most complicated equation that you may see in this course. Here, it involves modified Bessel functions of zero order here. These are some tabulated functions. We don't calculate it, but or we can calculate them. We can compute them using MATLAB, for example, or we can simply look at the table and then take the values and use them. So, probability of detection, as usual, as we have shown in previous slides, if we got a value, a function, let's say R, the envelope of the signal, let's say this is voltage, for example, or R simply, the random variable. If we got a PDF just like this, for example, then we can determine probability of this area. Let's say this is VT, probability that R R is greater than VT less than infinity, which means that if R involves a signal, then that's a declaration of signal detection. So that's probability of detection. So we evaluate this probability by using this rise in PDF. So we have to integrate this. This is quite complicated, so we do not give that. But this gives us probability of detection. Okay? Probability of detection. And mathematically, signal to noise ratio here from using one of the pioneers in radar systems, Spain, I think, I forgot the name, a researcher, formulated this and gives SNR versus probability of detection from this formula. It seems to be complicated, but we usually use graphs in here. The graph version of this equation will be shown in the next slide. So here then we got the relationship between probability of detection and SNR. And SNR is given in terms of signal voltage, yeah, the maximum of the signal, and the noise. Okay? So just like VT squared over psi. So here then, as PFA is related to SNR, PD is related to SNR, then we can draw probability of detection versus signal to noise ratio through probability of false alarm, because probability of false alarm also varies with the SNR. Okay, and it's dependent on the bandwidth. Okay, so we have to be careful. We got bandwidth, we got probability of false alarm, we got SNR, and we got probability of detection. All are interrelated. We cannot take one out and use the others if there is a signal. If there is no signal, just a noise, then we can talk about probability of false alarm and ignore probability of detection. If there is a signal plus noise, which is the case in every radar system, then we have to think about all these 4 parameters together. Now, note that here, SNR and bandwidth are simply given in radar range equation. Okay, so we simply go from probability of false alarm and probability of detection to radar range equation through SNR and bandwidth. Now, in this graph, we have many curves. Each curve represents PFA, probability of false alarm. So we determine a probability of false alarm and then determine the probability of detection for a given SNR. Okay, so here the design criteria will be PFA, PD, and SNR. Whichever is critical for us, we try to minimize it and then maximize the others, for example. Okay, so try to make a compromise in here. For example, let's take a probability of false alarm of, let's say, 10 to the minus 5. Okay, suppose that I can tolerate a probability of false alarm of 10 to the minus 5, which means that every one pulse or one decision out of every 100,000 decisions. Okay, that's the probability of false alarm that I can tolerate, for example. And suppose that the probability of detection that I can tolerate, for example, 0.98. So 98%. So I want to detect target echo signals at 98% on average. And how much SNR do we need now at the receiver side? So we just follow this curve, okay, and find the intersection of this curve with this value, okay, and then draw a line here to determine SNR, which is approximately 13.5 dB, right? Okay, I need 13.5 dB to get a probability of false alarm rate of 10 to the minus 5 at a rate of a probability of detection of 98%. Okay, by the way, 98% in practice is not acceptable. It's very low, actually. We usually talk about 99.99. So we have to go up and go here, for example. Okay, it's not clear here. For here, for example, this, we need about 14.5 dB. This is more realistic. So this means that 998 divided by 1,000. So every every 1,000 signals, I detect 998. Okay? That's how we read it, probability of detection. If I got 1,000 echo signals and I can detect with this rate, I can detect 998 of them. So missed only 2. Okay? That's a quite reasonable number. It can be accepted. Again, note that here the false alarm does not mean that we report a false alarm. False alarm rate is a number. We use this to estimate probability of detection, and we declare with this complicated processes. We declare there is a target or not. Is that clear? Now, can we relate all those parameters, right? Through some graphics, of course. We do not have a simple equation mostly. We have graphics, so then in any examination or any assessment, you will see some graphics, and you are supposed to use those graphics effectively to solve problems. Here is one such problem. Here we are given a radar system with pulse width and pulse repetition frequency and the operational frequency. And average time between false alarms specified as 30 minutes. Okay, and then answer these questions. What is the probability of false alarm? So PFA. What is the threshold to noise ratio? So VT squared over 2 psi 0. Right? And repeat A and B for an average false alarm time of a year. So in here, the TFA was 30 minutes. Now next, if you take TFA 1 year and then repeat this. Okay? What is the probability of detection then? And then we got PD. Okay? So you see, if we go back to the graphics, and then choose the parameters and try to read those values. Or alternatively, you can use equations. There are also some equations there. It's up to you. Mostly using graphics are much easier than using equations, if you can do. And we'll be giving all graphics to you if there's an assessment. Okay, next, pulse integration. Now, in previous analysis, all analysis we have done so far, we considered one pulse, single pulse case. In practice, we use pulse integration. Pulse integration can be implemented at different stages of the receiver. Basically, we do pulse integration before the second detector, which is called pre-detection integration, or we can do that after the second detector. It's called post-detection integration. So what are the differences? Let us try to illustrate that. If we got the signal at the input and at the output of the second detector, we can see the difference. Now, at the input of the second detector, we simply got a sinusoidal signal, okay? Just like this, okay? This is, for example, this represents a pulse, an echo signal, okay? An echo signal, but after IF stage, so it is the output of the matched filter, okay? Matched filter output, not a pulse, but a processed version of the pulse in the match filter. So this corresponds to somehow, this corresponds to this pulse, okay? Half of this. Now, next, what happens at the output. At the output here, we got envelope of this. So this one. Okay, let us make a plot, the envelope in here. So this envelope is this one. After the second detector, we got the envelope of this signal. So we extracted sinusoid. So pulse integration. If we do pulse integration at this stage, which means that I have two sinusoids, for example, just like this, and then add them up. Okay, what will happen? The magnitude of the pulse is sinusoids, if they are equal, let's say A and A, then the resultant sinusoid will have 2A amplitude. Okay, if there is a misalignment, then we got trouble. But mostly they are aligned, so we add them up to increase the voltage, so increase the energy, increase the pulse. So what happens when we do this after the second detector? We simply add envelopes, okay, not sinusoids. So if there is a problem at the detector, for example, let's take, this is perfect envelope. In reality, this envelope will be just like this. Okay, so if we add them up, these two envelopes, then we'll have some loss, because they are not aligned over the envelope, just like sinusoid. In sinusoid, we align them easily. We'll have very, very small noise as long as we get the peak values and align them precisely. So we got some loss because we simply add these two signals, for example. Okay, just an illustration. Okay, that's not the realistic version. So we got this one, for example, over time. So I just add this number with this one, and then add this one with this one. So they just, you see a variation, just like this, which means that we got loss. Okay, the total energy will not be the energy of the input or sum of the input signals. So what? How can we do this mathematically? Okay, the number of pulses returned from a point target can be written in terms of PRF, antenna beam width, and scan rate. It can be given via this formula. You see, the antenna beam width times PRF divided by the scan rate will give you the number of pulses from a point target. Okay, point target, be careful. For a realistic target, it could be quite different. But point target somehow models our system. So once we understand point target, we can extend this for other type of targets. So that's the simplest case. Then if we want to integrate a sequence of pulses, then we have to consider this number, n. How many pulses do we get first? And then we integrate them. If we integrate them successfully without loss, then the integrated pulse will be equal to this n. N will be the number of pulses to be integrated or integrated. If there is a loss, so if we use post-detection integration, then the number of pulses will not be equal to the number of pulses that we apply to the integrator. So here is where we apply integration. As we said earlier, here is the IF stage where we got a sinusoid here, and then this sinusoid here becomes, remember, a sinusoid again, a longer one, just like triangles. And then here we got the envelope of this. Okay. So let's now consider two cases: ideal pre-detection integrator and post-detection integrator. As we said earlier, the number of pulses integrated will be the number of pulses that we collect from the target, n. okay, in pre-detection integrator. So there is no loss in pre-detection integrator. N is equal to the number of pulses integrated. So what happens if we do pulse integration? We simply increase SNR. Okay? Once we increase SNR, we can simply reduce probability of false alarm. We can simply increase probability of detection. So the goal of pulse integration is to increase SNR. Okay? So how much do we increase SNR? By using pre-detection integrator. It's easy in here. We can use simply 1/n of the single pulse SNR to get the same false alarm rate or probability of detection when we use pre-detection integrator. Okay? How about post-detection integrator? In post-detection integrator, there is an efficiency. It's dependent on the integrator, and we'll be discussing that in the next slides. We define for post-detection integrator integration improvement factor, I, which is equal to the number of pulses, equivalent number of pulses. So we define NEQ, okay? In pre-detection integrator, if we write that, the number of pulses that we collect is equal to the equivalent number of pulses integrated. In here, it is not the case. Equivalent number of pulses integrated is less than the number of pulses at the input of the integrator. So this is critical. Okay, and it's very much related to the number of false alarms in here. So in next slide, we see the relationship. We got one false alarm out of every NF possible decisions within TFA. So we can remember the signal. In false alarm case, we have we got the time axis here and the voltage, and remember the signal just like this, right? So here we got TK, from TK we got TFA, and NF is the number of false alarms, so the number of pulses that is, the number of false alarms out of the number of decisions over the time interval that we do, that we make decisions, and it's related to the average time between the false alarms. It's related to the PRF. It's related to the bandwidth. So mathematically, the number of false alarms can be written in terms of false alarm time and bandwidth. It's simply inverse of the probability of false alarms. So here we see integration improvement factors for post-detection. This is pre-detection integrators. So the number of pulses integrated here, you see, is equal to the integration improvement factor, so 100. So you remember this, equivalent number of pulses integrated is equal to N, the number of pulses at the input of the pre-detection integrator. For post-detection, this, of course, this should be less than this one. We have 100 pulses at the input, but the efficiency here, so the number of pulses integrated will be much smaller than 100. Here we give NF, PD, and then this 2, we determine improvement factor. We read from this curves. For example, if we choose PD of 0.99, so 99%, and NF of 10 to the power 12, which says probability of false alarm is 10 to the minus 12. And then we see that the number of passes to be integrated is going to be 10, 20, 30, and 40. So only 40 passes out of 100 will be integrated, okay? So integration improvement factor here simply is dependent on the number of false alarms and dependent on the probability of detection. Once we choose the probability of detection and number of false alarms, we can determine integration improvement factor. Now we can define then integration loss, because as we said earlier, this was integration improvement factor, but it actually gives us how much loss we have out of 100 passes in this case. Out of 100 passes, we lost 60 passes actually. So inverse of this will give us actually the integration loss, which is usually given LIN. And using this, we can extend our radar range equation. And we, in the new equation, we use SNRN instead of SNR. In previous, remember, this was SNR mean. Now this is SNRN. SNRN can be written in terms of single pass SNR and then efficiency. Okay, so integration loss. So the new equation then involves the number of passes integrated, integration efficiency, and single pass SNR. So there are two new parameters, and the number of passes to be integrated and integration efficiency. So these two are related to the probability of false alarm and probability of detection through these graphs. And as SNR1 is also related to PFA and PD, so we have to make a compromise between PFA, PD, efficiency, passes to be integrated, and SNR for each pass. Okay, I think this was the last slide. Do we have any question?